Hey guys, I'd like to talk to you about dynamics today. Newton's law is a big part of that. We're interested in why things move, and obviously it's because you push on them, right? If there's a box, if there's a refrigerator, you got to push on it in order to make it move. So we need to think about all the forces that are involved and to come through and draw a little picture like you see right here. These are called free body diagrams. And on this box right here, you can see there's one force that pushes to the right and two to the left, and gravity's pulling down, and I've got a string or the table pushing up, something like that. I need to think about all the forces. So we're going to give this a try. Here's the skinny on what you need to know about this. We're talking about forces, which could be any kind of action. That's Newton's word here. This is Mr. Newton himself, and he used the word action. But today, any kind of push or pull would be a force. We measure that in a unit called newtons, and I'll tell you a little bit more about that in just a second. But 1 kilogram meter per second squared is what that works out to. First up, I need to tell you about mass. Mass is a measurement of how much stuff, how much matter. And, pushing on a refrigerator is not the same thing as pushing on a box of Kleenex, right? The refrigerator has more mass. It's harder to move. It's a measure of its inertia, how much it wants to stay in the same place. Acceleration, we know about that from having talked about kinematics, so that's all good. This is a new guy, a new player here. This is the Greek letter mu, and we use that to represent the coefficient of friction, just a number that says how much friction do I have between a brick and a wood tabletop versus a piece of glass and a wood tabletop, or your hand. And any two materials are going to have a different amount of friction between them. So you got to know what those two materials are, and that lets you look up this coefficient of friction. Okay, or problem will probably just give it to you. But either way, that's what that funny little U looks like. It's the Greek letter mu. Now, there's really only one rule in this game, one new piece of the puzzle, and it's right there. The sum of the forces equals mass times acceleration. That Greek letter sigma right there starts with an S, and it just means add up all the forces. And so that's pretty straightforward. Let me show you a couple little problems here, how this works. And right here we have a 4,000 kilogram car, and we've got a 300 Newton force pushing on it. I like to picture things, and our first step in this process is always to draw a little picture. So there's the car, and I'm going to write mass equals 4,000 kilograms to kind of take care of this number. Right here on the 300 newtons, there's a force. It doesn't say which way. I'm going to let it push this way. Force equals 300 newtons, and they want me to find the acceleration. So this is pretty straightforward. This is about as easy a problem as we want. Here's our equation, and I'm going to write that right here. Sum of the forces equals mass times acceleration. They want me to add all the forces. I look up here on my picture that I've already drawn, and there's only one force. So I could say, well, I've got that one force, and it's equal to ma. Maybe that's not quite necessary, but the force had a magnitude of 300 newtons, and the mass was 4,000 kilograms, and multiplying that by a. So there's the number. They wanted me to find a. Clearly, all I really have to do here is divide by 4,000 kilograms on both sides. That'll cancel that, leave that a all by itself. But what I do on the right, I've got to do on the left as well. So we're just solving this equation for a, and that's pretty straightforward. Here's a equals 3 divided by 4 would be 0.75. I'd have to move the decimal place one more time, but I'll do it on the calculator here. 300 divided by 4,000, and there's that 0.075 right there. That is the magnitude of my acceleration. It's speeding up a little bit. Each second it's going 0.075 meters per second faster than it was before. Here's a good place to stop and think about those units, and so I'm going to do that real quick. But you can see I've got newtons on top and kilograms on the bottom, and that's going to work out like this. Back on that last screen, we said that a Newton was a kilogram meter per second squared, and then I've got kilograms on the bottom. You can see how the kilogram on the top is going to cancel the kilogram on the bottom and work out to meter per second squared, which is fantastic because that's the unit that I want for acceleration. So I feel pretty good about that, and I'm going to put a box around it right there. Do notice that this force is pushing to the right, and we called this a positive 300, so we've kind of got a little coordinate system going on here where everything to the right is positive. When my answer came up a positive number, it means that acceleration is to the right, okay? If it had been negative, it would have been slowing down, but we're pushing on this car, making it go faster and faster. That's all we're trying to do here with Newton's law. It's pretty straightforward. I'll have some problems at the end that are a little more complicated, but it's the same process and the same idea. Here is the steps. These are the steps I'd like you to follow every time. You need to draw the object. Now, if you had two objects, you could draw both of them, right? Let's say there's a box and it hangs from a string, but that string goes over a pulley to a second box. See how there's two objects that are moving? The pulley's not moving, so we're not interested in it. The string's not an object per se. I've really got these two boxes. Let's call them M1 and M2. I need to draw that box, and then I need to draw the forces that are acting on it. So I could say, well, gravity is pulling down. We'll see that mg is how you calculate that. And the string's pulling up in both cases. We'll call it T for tension of the string. Okay? But that's what I need to do. I've got two objects, so I'm really interested in this right here, and I'm really interested in that. Each one of those is going to give me an equation when I go on to step 3 here and use Newton's second law for each object. So here's the first one, and then over here I would do it again for this object, and you can see how that works out. It looks complicated and lots of notation in the subscripts and all that, but really you're just saying, what's the net force on this thing? Once you've got those equations, then you're going to solve them. All right? Same process, every problem. Right here I've got another one. Here is a 4,000 kilogram car. I don't really need to draw a car. I could just draw a box right there. That's good enough. But I've got the first force is 300 newtons forward. I'm going to let that be this way. And then I've got a 200 Newton force forward, also in the same direction, not quite as strong. And 150 newtons backwards. You see how that picture just makes perfect sense of the problem? You're going to read the problem and you're going to draw that picture with 1, 2, 3 arrows on it because I've got 1, 2, 3 forces, and now they want the acceleration. I have drawn the object, I have drawn the forces, and now it's time to put them together in Newton's second law. And I could look up here and say, well, I got 300 newtons, I got 200 newtons, I got 150 newtons, and together they equal mass times acceleration. Don't forget your little coordinate system. Some of these forces are forward, some are backward. I would call that direction of motion positive, and anything that fights against that negative. The 300 adds speed. It's going to increase the acceleration. The 200 newtons, same thing. They're both going to be positive, in the positive direction. Meanwhile, the 150 is backwards. It's slowing me down. That's a negative. It's taking away speed. So I need a negative sign right there. The other thing that I should have done was filled in this mass right here. So let me fix that up real quick. And we will have an equation that's pretty straightforward to solve. Right there, that mass was our given up here, 4,000 kilograms. And that's multiplied by A. A is what I want. Got to get rid of the 4,000. I need to divide both sides by the 4,000 kilograms. It's going to cancel on the right and come out over here. like that. All right, I'm going to put some parentheses around the numerator to make sure all that addition subtraction gets done first. But I'll have parenthesis positive 300 plus 200 minus 150. Close up the numerator and then divide by 4,000. And I get a 0.0875. Okay. There again, I have newtons divided by kilograms, just like before. That's going to work out to meter per second squared. Nothing but A on the right-hand side of that. That's the acceleration that I want right there. Notice that it came up a positive number. Therefore, the acceleration is in the direction of motion, the forward direction. And we're all good. What would happen if this guy gave up being so contrary, so stubborn, and came over here and helped these guys? Well, you just turn that one arrow around, no big deal, right? Now I've got 300 to the right and 200 to the right and 150 to the right, and you can see that I've got 650 net newtons of force there. So when I add up all the forces, now instead of having 500 minus 150 would be, 350? I got 650, and I'd put that in here. 650 equals the mass, 4,000 times A, and I'd get a lot better acceleration out of this guy if they're all working together. To me, that makes sense, and it's just a matter of getting those signs right. 0.16, that's twice as much as before. Still not a great big number, but remember, it's just three guys pushing it. What is that? Three guys pushing on a car. Car's pretty heavy. You're not going to get it going at some crazy speed just from pushing on it. So it's necessarily going to be a small number like that. Does that make sense? Hope so. Let's see what else we got. Here is another problem, and this one says similar thing. I got a box. It's got three forces on it. It says the forces are 40 newtons to the right, 20 newtons to the left, and 15 newtons left. Okay. I don't know about you, but it looks like there's still more to the right than there is to the left. I've got a total of 35 left, but 40 to the right. So this box is going to keep moving that way. My acceleration is going to be that way. I always like to call the direction of motion positive and the opposite direction negative. It just kind of works out better that way. But I have my object drawn. I have the forces drawn. Now I'm going to use Newton's second law. Sum of the forces equals mass times acceleration. I've got a 40 minus a 20 minus a 15. Right here's where things get a little bit different. They gave me the acceleration. They want the mass. Find the mass. All right. So I'm going to leave mass blank and put in 3 for that. I'm getting kind of sloppy here and leaving units out. That's never a good idea. Maybe not. 2015. I've got a net force of 5 newtons, and over here 3 times meter per second squared, like that. You can see we're still just going to divide by the 3 on both sides, and 5 divided by 3 is 1.67. And the unit here would be newtons over meter per second squared. And we need to remember that a newton was a kilogram meter per second squared over a meter per second squared. So the meter per second squared on the top is going to cancel the one on the bottom, and we're just in kilograms. That makes sense because we were looking for a mass. So that's another one down right there. Same process. Okay. I need to tell you about a couple extra forces here that pop up some problems. One of them is called friction, and I'm calling the other one the downhill pull. And so let's say a word about these. Friction always slows you down. Friction is always a negative direction force because it's trying to stop your box, right? And what I'd like you to do is, if you have friction on a flat surface, pretend like that looks like a flat line, if you just put mu mg. Now, let's say I'm pushing this way, force of me, and the friction is a new force, a force that I have to account for on there. It's going to point backwards, but because this is on a flat surface, then all I need you to do is just put a mu mg. Mu is that coefficient of friction. It says I'm dealing with brick on metal, or brick on wood, or glass on wood, or skin on tabletop, or whatever it is. Those two materials will have more or less friction between them. So I need a number to say how much friction are we talking about. The mass of the object is there, and G, gravity, is what's pulling it down, causing that pressing between the table and the box here. So all three of those are there. Now, if it's on a ramp or an inclined plane, I've got to modify that just a little bit, and we're going to use mu mg cosine theta, where that theta is the angle of inclination, like that. When I tilt that ramp up at 20 degrees or whatever it is, then you're going to come in here and say, well, I'm dragging it uphill. There's me again, but friction is fighting that. But instead of mu mg, you got to slip that cosine theta in there. All right? If those are the forces on my boxes, then I would build the equation for this one by saying there are two arrows. So I've got the force that I'm putting on it minus the force of friction, and together that equals ma, just copying the right-hand side there. And that's my force minus mu mg equals ma, okay? And then I'd solve that. They'd give me most of those numbers. I'd plug them in, I'd solve for it. Over here, going to be the same thing. Sum of the forces on this guy equals ma. I got my force minus the friction, which is mu mg cosine theta. The higher you tilt this thing up, then the less friction you're going to get. So that takes care of it right there. It's equal to ma, and I'd get that equation. I'd fill in the numbers and solve for it. Now there's really one more force that should go on this picture right here. Not this one, but anytime you have a ramp or an inclined plane, that's the fancy name for it, a tilted up flat surface, inclined plane, or a hill, anything like that, this box right here, gravity is going to try to slide it downhill. And we could draw all kind of vector diagrams and show you where that piece exactly comes from. But what I'd like you to know is that you can always just draw that blue downhill arrow there, call it DHP if you like, but it's going to be equal to mg sine theta. So really when we do this one right here, my direction of motion is uphill, my force is uphill, that's a positive. We've already got the friction fighting that. The friction should always be negative. This downhill points in the same direction, opposite the direction of motion. So I really should have a mg sine theta on there. And all of that on the left equals ma. And again, they're going to give you the numbers, you plug them in, and you do the thing, all right? So I got I got a list here of all the forces. Here's those two that we just talked about, the downhill pull and the friction. So we kind of know if we see something on a ramp, to go ahead and put the mg sine theta pointed downhill. We know if there's a coefficient of friction in the problem, then to go ahead and put some friction on there. If it's flat surface, mu mg. If it's a tilted surface, a ramp, then it'd be mu mg cosine theta. I didn't tell you anything about this, but there are weird cases where maybe you've got a box on a flat surface. So normally, you know, if I'm pulling this way, then the friction would point this way. However, if I'm pulling up at a little bit of an angle, then that's going to change what we call the normal force. See how I'm lifting up on that box? That's going to lighten the load. It's going to make less friction down here. So I'd really have to go through and find this thing called the normal force, multiply that by mu and do the friction that way. I don't need you to do all that, okay? If you can just put mu mg on a flat surface, mu mg cosine theta on a ramp, we're good to go. All right, but these are the other forces I'd like you to consider every problem you do. Is gravity an important thing? Well, gravity pulls down on everything near Earth. So generally, yes, here is a book on a table, and gravity is going to pull down on it. And you can see that to calculate gravity, I just put mg. So that looks like that. But I also have a force called the normal force, which is the table pushing up. This normal force is the table pushing up, or the ground pushing up, or some kind of substance. If you hold a hamburger in your hand, right? Gravity's pulling down on the hamburger, your hand's pushing up on it, and guess what? Those two are going to cancel out. If they cancel out, they go away and nothing really happens there. So we don't really need to put those every time unless there's some kind of weird extra upward downward force, all right? But so sometimes we're going to be really interested in mg, and sometimes the normal force cancels that out. We don't worry about it. Let me show you what I mean. If I come in here and take the table away, gravity is still pulling downward, but now there's no upward force. So I wouldn't even draw this in like that, and that would be the force. If you drop a rock, that's the picture, right? Here's the rock, and gravity pulls down on it. There's only that one force. Or maybe you've got a string on it. Maybe there's a string that pulls up that holds this thing. T for tension right there, okay? So you kind of got to go through each problem every time and say, do I need to put gravity? Do I need to put a normal force? If so, do these two cancel each other out? And if they're both there, they usually will, for us especially, okay? The tension, is there a string involved? Maybe there's a string pulling this way. I'll put T2 for the second string, all right? Is it on a ramp? Do I need to put a downhill pull? Is friction involved? You know that there's friction anytime you see that mu right there. And then is there anything else? Is there a person that's back here pushing on this box trying to make it go that way, right? The force of the person. What else do I need to put in my picture? This little checklist is the best way I know of to kind of make sure everything is accounted for and taken care of. I've got a couple problems here. Let me just work these and you'll kind of see what I'm talking about. Here is a 4 kilogram hanging box. It's held up or pulled up by a string. That string runs over a pulley to a second hanging box with a mass of 11 kilograms. I need a picture. I got a box here that's 4 kilograms, and I got another box over here that's 11 kilograms, and there's a string that runs up over a pulley to the second box. I'll draw the pulley in here, but the pulley's not moving, and we're pretending like that's a perfect pulley, that it doesn't have any friction, any mass, no moment of inertia to make it turn, anything like that. So it's just this picture right here, and I need to go through the list for both of those objects. And I could say, does gravity pull down on the first object? And I go, yeah. There's the gravity pulling down on mass 1. I'm going to call this guy mass 1, and this will be mass 2 over here. Okay? So I'm going to put that one. Is there a table pushing up? No, it's just hanging in free space, so I don't need the normal force, but there is a string, right? See how that string is pulling up right there? So I need a T for tension on that guy. Is it on a ramp? No. Is it rubbing against something? Is there any coefficient of friction? Are there two materials in contact with each other? No. Okay? Is anybody reaching into this problem and pulling up or down or anything on that? No. Okay? So see how the little list just kind of helps you get your picture right? The hard part of this is getting the picture right. Because now that I have my picture, now that I know that the only forces I have to worry about are the tension and the weight, then I build my equation. Sum of the forces on mass 1 equal mass 1 times A, And I'm putting those little subscripts just because I'm going to have to do the same thing for this box over here in just a moment. But all I want to think about right now is that box and any forces that are directly on it. Gravity's pulling on it, the string is pulling on it. And so I make a list of those two. I got T and I got M1G. Together they equal M1A. You can see that they're in opposite directions. So I need to think about which one's positive, which one's negative. In order to do that, I have to know what the direction of motion is. Well, that's pretty easy to guess. Here's 4 kilograms on one side. Here's 11 kilograms on the other side. Gravity's going to pull down on this more than it is on this. So this guy is going to go down. That's my direction of motion, and therefore my coordinate system. For this guy, I would call down positive. But that's going to pull the string down, which pulls this string up, which pulls the box up. So this box is going to go up. That box is going to go down. And I need those coordinate systems to match up with the individual boxes. The T is pulling up, which is positive. Put a plus sign right there. And gravity is pulling down the opposite direction. So he gets a negative sign like that. All right. When I do my numbers, remember this was 4 kilograms. That's really the only number I have. So I'm going to go T minus 4 kilograms times 9.8 meters per second squared. There's that acceleration due to gravity G. I've got 4 kilograms right here, and then an A. But I don't know what T is. I don't know what A is. That's two unknowns. So I can't really solve this equation. All I can really do is kind of simplify it down. That 4 times 9.8 would be nice to straighten out. Get all those numbers together. That's a 39.2. So about as simple as I can make this is T minus 39.2. I'm even going to leave the units out here, equals 4A. That's the equation that governs the motion of that box on the left. Its box and the two forces on it. Now I got to do the whole thing again, but for this box on the right. So I got to run through the list again. Does gravity pull on it? Yes. Put an arrow. M2G. Does the normal force? No, there's no table. Neither one of these has a normal force pushing up, but both of them do have a string, and in this case the string runs up opposite the direction of motion. That string is holding back. If I didn't have that string there, if I were to come in here and cut that string, then this box would just fall like a rock. Because it doesn't, something's slowing it down, and it's the string that's holding it back. It's the string that's pulling in the negative direction right there. So I definitely need that. It's not on a ramp. It's not rubbing against anything. There's nobody pulling on it. The only two forces I need for both boxes are the weight pulling down, the tension pulling up. I'm going to build the other equation right here beside the other one. And again, all I'm doing is looking right here at the box and any forces that are directly on it. M2A, I've got T, I've got M2G, that's equal to M2A. Let's put the numbers, well, let's get our signs in there first. We said the direction of motion is down, so I need a plus sign on anything that points down, like M2G. Opposite that, holding back, slowing down, taking away speed, is this tension. So it gets a negative sign right there. Both boxes have to move in the positive direction. These two boxes are tied together by a physical piece of string. They need to be mathematically tied together with a coordinate system, and that's the way to set it up. Okay, I'm going to put my numbers in. I don't know what T is. M2 is 11. G is 9.8. M2 is 11. I don't know A. Looks like that. And 11 times 9.8 is 107.8. So let's simplify this thing down as much as possible. It's going to look like that. And I'm going to put a little box around that. I would like the solutions to those equations, but I can't solve the one in black. I can't solve the one in red. What to do? Well, here's what you do. You take both of them, and we're going to do some form of simultaneous equation. There's lots of options, but the easiest thing is to stack them up and just add straight down. The reason that works is it's perfectly okay to add the same things to both sides of an equation. I could add 7 to this and 7 to that, and it'd be balanced up, right? Well, that equal sign says that all of this is the same thing as that. So if I add this to that, add this to that, then I'm adding the same thing to both sides. And that's perfectly legitimate. Here's the t minus t. Those are going to cancel. And I'm going to tell you right now, if your t's don't cancel, it means you goofed up your coordinate system. So go back and look at it and make sure that both boxes move in the positive direction. This box is moving down, so down is positive. All right, over here, I've got 107.8. Put in the bigger positive number first. You don't have to, but minus 39.2. I'm adding straight down, so I want to keep the signs. That's a 68.6. Adding straight down 4a plus 11a would be 15a, and all I got to do is divide right there. I'm going to get a 4.5 or 6 something. I already got the 68.6 divided by 15 is 4.57. I'll go ahead and put this step in. I'm getting a little ahead of myself here, but I want to divide by 15 to cancel that, leave the a by itself, divide by 15 right here, and that's where I'm going to get that 4.57333. I'll leave the 3's off. That is the acceleration. It better be meters per second squared. We've already seen that these are all newtons, and a newton divided by a kilogram here, which this is going to give us the meters per second squared there. All right, so make sure that you got all the units right going into this, unless you want to put in the units and see what happens. I like to keep it as clean as possible. I should put in the units, but I didn't. Okay, yikes, made it a little bitty. Come here. You can't see that. All right, so that's that problem. There actually is one more thing we could do here and learn about this. There's got to be some tension in that cable, right? If I hang enough weight on this thing, it's going to break the string, or if I have a string that's not strong enough, it's going to break, and both of these are going to fall. Sometimes they build elevators like this, right? So I got a car full of people over here and a big heavy weight on this side. If that cable breaks, that's bad news. So engineers have to go through and think about, well, how strong of a cable do I need? And all you have to do, now that I know A, I could either plug it in right here, or I could plug it in over here and solve either equation for T. Okay, this one's a little bit easier because I don't have to deal with that negative sign right there. So just to show you what I mean, if I take that first equation, the red one, T minus 39.2 equals 4a, but now I know the value of a, so I can put that in like that. On the right hand side, I'm going to do this, so that would be 4 times 4.57. That would be 18.28. T minus 39.2 equals 18.28. And all I'd want to do is add 39.2 to both sides, which would cancel it on the left here, and then I'll have T all by itself just like I want. T equals what? I don't know. Let's add, let's see, 39.2. Okay? There's a 57.48. If my cable, my rope, string, whatever that is, can't hold 57.48 newtons, then it's going to break and fall, and the people in the car are going to scream all the way to the bottom. All right? And then they'll stop screaming. So make sure that you know, sometimes it'll say give me A, and you could stop right here. If it says T, you got that one extra step, and no big deal. You're just filling in the numbers. Okay? That looks like a whole bunch of craziness on there, but it's really not that bad. You've got your list of variables, not variables, list of forces here. I sometimes call these the usual suspects. Um, you kind of run through that list and say, which ones do I need? And once you've got that for each box, then you're going to build an equation for each box. You're going to cook that down simple as you can, stack them up. The t's better cancel out, otherwise you goofed up your coordinate system, and you should only have one variable left. You solve for that. If you need the other one, you go get it. All right, good. Here is one more problem, then we'll do a little summary of the whole thing, and I'll send you on your way. If you have questions, you want to work with these, then just bring them up in class or contact me. I've got a box on a 20-degree ramp, so let me draw that part. There's my 20-degree ramp and my box. I'm going to put M1. First mass they mention is 4 kilograms. I'm going to put theta equals 20 degrees. Okay, that takes care of those numbers. There is a coefficient of friction of 0.3. Okay, so I'm already thinking, coefficient friction, I'm going to have one of these. And I go, ooh, it's on a ramp. I'm going to have a downhill pull. And then they say it's pulled uphill by a string. Ooh, I got a tension. You see how the forces kind of start to come in there? I'm going to draw the string before I think about the forces, but there's a hanging box over here of 11 kilograms. So these are the same numbers we had before. The setup was different. We didn't have a ramp under there before. They just both hung straight down. But it's going to be similar, just the pictures are going to be a little bit different. That means the equation's a little bit different. We're looking for A. We don't have to do that second step and get T here. But let's just run through each one. I'll take mass 1 here. Does gravity pull down on it? Yes. It would look like that. Does the normal force push up? Yes. It looks like that. Those are going to cancel, and it's not quite that clean, but almost. I'm going to let those two cancel each other out and not put either one on my picture. What I definitely do need to consider is that tension pulling uphill and the downhill pull. It's on a ramp, so I got to include that one. And because there's a coefficient of friction, I got to get in a frictional force right there. Now remember that they told me that this is getting pulled uphill. So my direction of motion is that way, and the direction of motion should be positive. So T is a positive force. The downhill pull is fighting that. I'm having to overcome that. Downhill pull is slowing me down. Gravity wants to slide it downhill. I want to slide it uphill. Opposite direction. Friction is always opposite direction. Friction's always fighting me like that. But you can see how an equation is just going to fall out for that right there. The sum of the forces on mass 1 equal mass 1 times A. I've got 3. Oh, and nobody's pulling on either box, so we can just leave that one out. T minus DHP minus F sub F equals M1A. Okay, that's my first equation for this box. I can fill in some little gaps here. I know the downhill pull was mg sine theta. I know the force of friction on an incline, mu mg cosine theta, and that's equal to M1A. So let's see how much of that we can fill in. I've got, don't know T, mass 1 is 4, G is 9.8, the angle was 20 degrees, so I've got a sine 20 right there. Coefficient of friction is 0.3 times 4 times 9.8. Cosine theta, I'd have to do cosine of 20. And that's all equal to the mass, which was 4 times A. Can you see how nice the picture is? All of those numbers are right there. All the forces, I go 1, 2, 3, and there's 1, 2, 3, uphill, downhill, downhill. It just falls into place when you've got a good picture. And if you don't have a picture, good luck getting any of these right. You got to get that picture done up first. All of this that I'm underlining here is just a dumb old number. So I can take my calculator and simplify all that down forthwith, I'm going to start with that negative sign right there because it's a negative force. Negative 4 times 9.8 times the sine of 20. Please make sure you're set to degrees, not radians, right? Hit that mode button, find out if you have any question. Close up your sign, and then go minus 0.3 times 4 times 9.8 cosine 20, and all that stuff that we underline turns into a negative 24.46. So let's do that. T minus 24.46 equals 4a. That looks a whole lot better, doesn't it? Okay? Get rid of all those sines and cosines. Let's think about the other box. We've gone as far as we can. With those two unknowns, we're kind of stuck. But when I come in here, I'm going to run through the same list again. And I say, I do have gravity, but there's no table pushing back up. So I don't need the normal force for either box. It's going to cancel out on this guy, right? And there is no table here, so I don't need any normal forces. Do I have a string? Absolutely. Just like the last problem, that thing is hanging from a string. It's moving down and it's accelerating as it does that. But there's that T. I got the M2G right here. So I got those. It's not on a ramp, so I'm not going to have a downhill pull. It's not touching anything, so there's no friction. Nobody's yanking on it. So we're good to go right here. And I can say the sum of the forces on mass 2 equal mass 2 times A. I have those two forces, the T and the M2G. Together they equal M2A. Just copying the right-hand side. I need to think about my coordinate system. We said this box is moving uphill. That's going to give me string here, so this goes down. The direction of motion is down, so down is positive. M2G gets a plus sign, and tension is in the opposite direction. Opposite the direction of motion needs a negative. Notice already that I've got a plus T here and a negative T there, so that makes me happy because I know those T's have to cancel out. Negative T plus 11 times 9.8 equals 11A. Wonder what 11.9.8 is. We just did that actually on the other problem. It was 107 something, 107.8. So here's negative T plus 107.8 equals 11A. I got a second equation that I can't solve by itself, but guess what? When you stack those things up and add, it should be pretty straightforward. T minus 24.46 equals 4A, and negative T plus 107.8 equals 11A. And I want to add straight down. T minus T cancels out. I've got a negative, come here. I got a, we'll do it the other way this time, negative 24.46. Just make sure you get that negative in there, and then the plus 107.8 works out to 83.34. Adding straight down, I'd have a 15A. I need to divide both sides by 15. Looks like that, and I got a 5.56. That's going to be meters per second squared of acceleration. That's the number that they want right there. Okay. These last two problems are a little bit involved. Okay. But if you use your list of usual suspects, and if you draw a picture of each box, and if you draw the forces on each box, and if you use those pictures to build the equations for each box, then it's pretty straightforward. This is a very common sense kind of thing. You got to know what forces are acting before you can add them up. So use your picture to do that. Here is the summary then. You've got your variables, force, and newtons. Remember how force was equal to ma? If my mass is in kilograms and my acceleration is in meters per second squared, Can you see why 1 kilogram meter per second squared is that quantity that we call a Newton? It's all right there. We're going to do this on every problem in this unit, this section. You're going to always draw each object. If you see anything about forces, you need to draw a free body diagram. So draw the object, draw the arrows representing the forces. You got to do that for each object, and then build the equation, solve the equation. Here's your list of possible forces one more time. And if it were me, I'd try to get most of that on a card somehow in a manner that made sense to me, as condensed as possible. But you can do these, and whatever you have questions about, you need to bring those questions to class or ask me outside of class or something, and we'll get through this, okay? So thanks for stopping by, and that is Newton's Law and dynamics. Have a great day.